All right. Welcome back, everybody. Sorry, I'm a little bit late today. There's this visitor I need to meet. So I'm gonna today, as I said, I'm gonna do a review. The review would be basically based on your feedback last week. I'm gonna talk a little bit about blockchains first, and then I'm gonna talk a little bit about crypto, advanced crypto. Then I'm going to do actual kind of like a very quick review and then some discussion on actually, I'm going to do also what we do as our research. And then the fourth thing would be just a quick review of things that we learned and some trivia and then some discussions about the final exam and so on. Is there any question before we get started? Good. All right. So blockchains. So this is going to be your fifth CA, which is going to be out soon, and then I think the deadline would be next Friday. I'm basically to kind of give you a quick rundown. So of course, blockchain is its own course, multiple courses actually. So I'm not gonna try to kind of cover trying to pretend that we're gonna cover like a decent amount. But I'm just going to give you like a very basic idea of the important parts of a blockchain. And it's actually borrowed from this course from Dan Boone, which is kind of a very prominent cryptographer at Stanford. This is actually, he offered a proper blockchain course, CS251. And this is the first lecture of his class. I actually made some modification to it. But if you're interested, actually all of his lectures and videos are available online. You can go and check them out. If you're joining, Stanford anyway in future, you can actually go and take his course. But yeah, so what is a blockchain? So blockchain is essentially just the abstract answer for blockchain is that it provides kind of a coordination between many parties without having a single trusted party. Okay. Generally, the kind of the format of a blockchain is that if I don't trust anybody, if there's no single trust party, then in order to kind of do something useful, I need to kind of distribute the trust. And then the idea of the blockchain is that. And then you can think about why we don't have single trust units. Sometimes there's no one that we can trust. For example, I don't want to trust the banks. I don't want to trust the government. So I will go with like a, distributed trust. Sometimes just the format of your system force you to have a distributed trust because just everything is linear. So not all the blockchains are necessarily like a public and everybody use blockchains. It's also sometimes blockchains are just internal to a company. For example, IBM has its own blockchains for, let's say, supply chain. And they use it in order to make sure that the trust is distributed. So it's not like a single failure kind of design. So just something to remind that, blockchain sometimes is more of like a grand scheme of like, conspiracy theory kind of things of blockchain. Sometimes it's just actually using even in companies when there is a central trust. Okay. And then the main things about blockchains, of course, is, Bitcoin and financial systems. And that's where kind of like the killer app of blockchains kind of, born. And probably all of you have known about Ethereum and Bitcoin and so on. That's where kind of like the main motivation of blockchains exists. But just keep in mind that blockchains exist in many, many other systems as well, not necessarily for financial systems. It's kind of like, what was the idea and where it begins? As I said, Bitcoin was kind of like it was the first time that, the idea of blockchain was kind of like, born in 2009. And then the main innovation that kind of gave birth to blockchain was using this, what we call append-only data structure, that you can always just add things to it, but you cannot easily remove things from it, okay? And then the nice thing about this append-only data structure is that everybody can verify it easily, okay? So if you can kind of like, append things to it and distribute it, replicate it throughout different users, and then can easily kind of verify the existence of things and then make it very, very hard for removing things from it, then you have a trusted database, right? So then everybody can now know that what happens. And then this could be, for example, transactions of your financial transactions. So in other words, you become a bank, right? And then, but this bank is not a single unit that everything is there. Is actually, it's distributed. Everybody has a replica of this transaction list, and together they can verify things. And then the important things about blockchains is that there should be incentives for people to kind of participate in this game, right? Because once you decentralize things, then you should provide incentives. So if you kind of like, do some service to this blockchain, you should receive some incentives. And that's the idea of what we call miner, right? So by doing mining, you receive some Bitcoin in, for example, in return, and there's also or receive some reward in return, which in most cases is financial incentives for players in this game. Okay. And if an adversary tries to kind of attack this system, which there are many, many attacks in blockchain systems, the idea is that, since this is an append only, and it's very, very hard to kind of remove information, one cannot really attack the system. This actually, the nice thing about blockchain is that it relies on cryptography. And as we discussed many times in this class, the nice thing about cryptography is that you can get actually mathematical guarantees about the system. So essentially, like, security of something like a Bitcoin is based on this fact that you cannot really do hash. You cannot find collusion for hash functions, for example. One of the reasons that the system is secure. Okay. And yeah, and then you can use it for digital payments and all as well. So if you kind of build like layers on top of this kind of base layer of a blockchain, then you can actually use it for like receiving payments, getting payments, and all those things. Okay. And then there's not just one type of blockchains. There are different types of blockchains with different kind of like, different differences. For example, the big difference between Bitcoin and Ethereum is Bitcoin uses what we call a proof of work, versus Ethereum usually use what we call a proof of stake. I'm going to actually describe a little bit what is a proof of work, but generally it's just all based on this fundamental assumptions that we use some form of append-only data structure, replicated, and to provide incentives for people to use. Okay. And then essentially you can have kind of like what we call a blockchain computer, which it's something that you can actually program it and do things. So you can actually run different functions on the blockchain. And I'm not going to go through that part of blockchain. As I said, this is like a very, very vast area, but you can do arbitrary things on the blockchain. This is actually Turing complete, functions. That's very, very powerful. It's not just, sending and receiving Bitcoin. It's actually, you can do many, many things using blockchains. Okay, just keep that in mind. And then, so this is kind of like, again, the involvement and improvement of blockchains, and starting like 2017 all the way to now, we have things like NFTs and other things that essentially it's just expand the use case of blockchains from just Bitcoin to other things as well, right? So probably you're familiar with this. So as I said, the basic application, the reason that blockchains is useful, as I said, is usually digital currency, Bitcoin and Ethereum. And there are a whole bunch of, probably, how many of you have bought Bitcoin stocks or Bitcoin at some point in your life? Yeah, so you're already familiar with a little bit of it. Did you make any profit? Who made some profit? You did?
You mined it, so.
You mined it?
Free, yeah.
Nice. When?
Back like last year when it was, 2022.
Okay.
It was still kind of.
How did you mine it?
They have this program called Nice Hash,
Mm-hmm.
and so I just installed that, and then I just left my GPU running.
At home?
Yeah.
Did you see?
This is like a good $600 just for leaving my computer running.
So once you mine, you get $600, or?
No, I was that thing was running for a while.
Oh, okay.
Yeah.
All right. Yeah. So I mean, like, big thing about mining these days is mining is. So you made money, but not overall. Your household may not make money, right?
On it, like how much you pay for electricity and like how much it costs to mine. So I came up on top. Yeah.
Okay. All right. So we trust you. But yeah. So I mean, this is something. What happened? Oh, season, yeah, I think,
Smart would just need to use the dorm's electricity.
yeah.
Way.
You're already paying for university apartments, you don't pay utilities.
Yeah, exactly.
Yes, I don't approve all of these things. Given that it's also recorded, so it's completely fraud upon. By the way, yeah, I think there are actually rules that this is technically illegal, so just be careful. There's also, yeah.
So we can give you a cut.
It's being recorded now. We can talk offline. No, but seriously, it's make sure that you follow the rules always. Especially when you're like in UCLA dorms, you have to follow UCLA network, because you technically signed the agreements. And then also joking aside, there's actually kind of crypto mining is definitely a big issue. It's not like, it's not like our idea. It's something that many people have used in the past. And there are these malwares called crypto jackers that, yeah, you download a file, and if you remember, we talked about different types of malwares. One malware that is kind of being very, very popular these days is this crypto jackers. That essentially it offloads one of these applications like Nice Hash or whatever. There are like lots of these kind of packages that you can download and use. That it basically runs off your computer without you knowing about it, right? So you like all of a sudden you see that your computer is kind of being used, and then it's because you kind of some malware has been downloaded on your system. Another thing that people do is they're actually doing this crypto jacking detection algorithms. That since crypto has this very repetitive and kind of known pattern, like similar to the way that we did for network intrusion detection, malware detection, one can also use it to detect crypto jacking. Right, so I'm hoping that UCLA, for example, runs something like this on their own networks. But yeah, it might be detected based on that. You had a question?
That happened to me. I leaked the keys to my CS35L project. And then I went to sleep after I submitted it. And then I got like 50 emails from Google Cloud at 5 a.m. But they had a security thing where they detected behavior that looked like crypto, and they cut off my account before I was charged.
There you go. Yeah, so they have like crypto miners. There are hardware methods for crypto miners. Now there are software methods for detecting crypto miners because of this big issue. But yeah, it's interesting to see that it actually exists. Anybody has any other comments? Okay. Yeah, so I mean, but it's not just crypto, Bitcoin and financial. There's also other things such as DeFi, asset management like NFTs, decentralized organization DAOs, and then a whole bunch of systems. And then, as I said, the third thing and a very interesting thing is this a new programming model based on what we call smart contract. And then you can actually write decentralized programs to actually do something useful without having any server. So many of our systems, like in this course, mainly we say that there is this IoT and cloud continuum, and then you kind of offload things to the cloud. If you don't have that and you want to write things in a decentralized manner, you can actually do that as well. So if you're interested, definitely take a look at like how do you write smart contracts and so on and so forth. All right. And then again, this is kind of like, volume of these different numbers and number of developers, and then the fact that how much these things are getting very popular these days, and then of course it's kind of like this part of the course that I'm still like borrowing the slides from, so it's kind of motivation of people to learn more about blockchains, and I definitely recommend you to take spend some time and learn more about it. And as I said, like another big motivation is kind of like if you don't trust your governments and you don't trust your big, corporations and so on, blockchain is a way of kind of combating against those, right? So it's more of a global level of things. This is helpful for that as well. So as I said, blockchain is not just one layer. As I said, the kind of the consensus layer or the kind of the data availability layer is what we know as a blockchains, especially the crypto part of it. But there are a whole bunch of other things that kind of builds on top of it to actually build a real blockchain. So for example, if we talk about something like, a Bitcoin system, there is like this underlying backbone of Bitcoin, which is like this ledger and how we actually create the blockchain. But without having a proper layers on top of it, you cannot really have a real transaction, right? So when we're talking about blockchains, you actually need to know everything about this. These upper layers are essentially some sort of, you can think about this as any other server system, right? but it's domain specific to blockchains. But the part that is kind of innovative in sense that kind of enable blockchains is kind of like this bottom layer kind of, okay? And then, as I said, if you're interested, if you take the course or watch the lectures or just read the books, you will learn about all of these. We're gonna just briefly talk about this like bottom layer very quickly in the next few slides. The rest you have to figure it out and learn about it yourself, okay? So what is this kind of consensus layer? What is this like lower data availability? Is there any questions or are we good? Okay. So very informally, this is what we call a public append-only data structure. The reason that it's public, it means that everybody can kind of like have a replica of this. Alternative, this would be a private, data structure. Not necessarily every blockchain has to be public, but we are mainly talking about public because that's the whole point of having a decentralized system. So there are four important things that you're looking for in a consensus layer as well in a secure blockchain system. The first one is persistence, which means that once I add a block, it's not easy to remove it. And this is achieved, as I said, by replications. Usually you need to kind of convince 51% of your network in order to remove something. And again, mathematically, this is hard to achieve with a regular system and so on. That's why you have persistence. And then you need to have safety, which means that all honest systems have to have same data. Of course, if everybody changes their data, then your system won't be secure. It should be liveness, right? Which means that you should be able to add new things. Otherwise, you have a static blockchain system, which is not helpful in many cases. And as I said, it should be open, which means that everybody should be able to contribute, especially if this is a no trust system. In order to kind of be able to contribute, you should have just follow a particular protocol and you should be added. Otherwise, if it's kind of like saying that you can add and you cannot add, then there's nothing open and public about this. Okay. So how we actually adding things to blockchains? Adding things to blockchains follow a specific pattern. Usually, I'm going to actually describe this in more detail, but different users have their own secret keys. They're going to sign things and send it to the blockchain. Blockchain, as I said, has different workers, which we usually call them miners. Each one can verify a block. Eventually, usually one miner decides to do that, and if they can, verify the block, and I'm going to describe how do we verify a block, then they receive some incentive from it. So, for example, in blockchain systems, the incentive is different than Ethereum, system, and so on and so forth. That's how your friend actually got some money out of this, right? Important thing is that you have many different miners, so knowing which one can verify things becomes tricky, right? Because all of the miners try to mine, and of course all of them have incentives. As a result, they become a competition between the miners, right? So you want to obviously to achieve mine as much as possible. The other competitor also wants to do the same. So there should be some form of mechanism to decide who is kind of the quote unquote leader, who is mining and who others are just verifying, because the leader is usually the one that receives the incentive. Okay. So that's where we have this thing called consensus, because consensus is that eventually we want to have a uniform and same copy of the transactions, all of them, right? Because this is a decentralized system. Eventually, everybody should have the same copy, right? In other words, everybody should have a consensus on what is a current version of our blockchain. Think about it. Everybody kind of modifying a shared document. At the end, there should be same document that everybody knows, right? So the simplest way you can think about this is that all the copies are consistent. That's when we have a consensus, right? So everybody receive kind of request. So let's say, for example, this is a very, very nicely kind of distributed system. One request goes to one miner, the other request goes to the other miner, and so on and so forth. And then they all kind of talk to each other properly, and everything's kind of sent at the same time. As a result, all of them at the end of this kind of 4 transactions going to see the exact same kind of patterns list, that all of them see TX 1, 2, 3, and 4, right? This is this is the ideal version. But unfortunately, this is not what we see in real life because of various different reasons. For example, there are network delays. So for example, this one, if from sending here to here, there is delay, but maybe from here to here, there's no delays. So they see like either different order of things, or maybe even some packets might be dropped and so on and so forth. So we're not going to see the same kind of like, order in all of these. And then in blockchains, order matters a lot. So that's why it's very important to have this consensus layer. So basically one thing that could happen is that network layers affect the order of things. And that's important because in some cases, order is very important. Another thing that could happen is that not necessarily all the miners might be within one network. They might not be able to kind of communicate to each other. So in some cases, for example, these two guys can talk to each other, but they cannot talk to other miners in the different network. So in other words, what will happen is that these two guys see the same copy, but the copy that they see is not going to be the same as the copy that the others see. Okay, so that's another problem. Another problem that could happen is that some of these miners might crash. Like if the request is kind of goes through one of the miners, and then in the middle of verifying it crash, we need to figure out what will happen to this request, because this request has to be kind of like serviced. And then finally, you can have a malicious actor in the system. Since this is a decentralized model, we're not really kind of verifying or vetting anybody as a miner. Any player could play in this game, including adversaries. So what will happen, for example, if the adversary tries to kind of like, provide false information, not playing the game, kind of doing various different things, right? So malicious behaviors. So this is what we call a consensus layer, and there are lots of solutions on how we actually do the consensus. As I said, I'm not going to talk about the details of this, but this is again consensus layer, and how do we actually build, how do we fix these problems is the story, one of the biggest stories in blockchains. Okay, there are lots of network and protocols layers involved in order to make sure that this system is indeed fixing all of these issues. Okay, the second thing is the blockchain computer. As I said, you have different decentralized applications or dApps, and these things are written on the chain and being executed on the chain. And then all the transactions between different applications also recorded on the chain. And this is what we usually call a blockchain computers. Again, this is very, very interesting and exciting things. This is less known part of blockchains, that most people, when they say blockchains, they know Bitcoin, but they don't know that you can actually run various different applications. So definitely take a look at this. In order to explain how this works, we need a lot of background. So I don't want to talk about this today, but just know that such a thing exists. Maybe at some point you can take a look at it. And then lastly, you have usually a layer up on top of it, which kind of like the top layer, which is kind of the server layer. And this is usually, as I said, it's regular server kind of interaction. So users really not talking directly to, I don't know, miners or computers. They're similar to any other systems that we have in computer systems. They talk to a server, and from the server, it goes to the individual kind of miners or individual computers. Okay, so this part is no different than any other systems that we discuss in this class so far. So think about this as like your IoT nodes, and then the server is essentially the one that you talk to. Okay. How many of you has anybody ever do any transaction with Bitcoin before? No, you did. So do you remember what server, like what did you use, where do you log in, so stuff like that?
My country made it its currency.
Oh, okay.
It was just like they have an app that you use.
So you use an app and then you log in, and then there you see. So that's kind of like it, right? So that app was connected to some server, and then on the back, in the back end, there was actually kind of like this blockchain. So you didn't really kind of like doing these things. You just kind of do it normally, right? Like any other app, you just kind of receive money, send money, and stuff like that. Yeah, exactly. Okay, so there's like these layers that are also part of the blockchain. Just keep in mind. So let me actually talk a little bit about kind of the underneath kind of cryptography layers of like what's the magic part of blockchain. And as I said, there are two main things that you already know, both of them. One is cryptography hash functions that we discussed in class, and the second is digital signature. So these two things together is actually really the workforce and the main fundamental part of any blockchain. Okay, so we already know about hash functions, but to just kind of review a little bit what's useful for your class as well is cryptographic hash function is an efficient function that transfer a message from a message domain M and transfer it to a domain T or domain hash. And the big thing about hash function is that it reduced the size of the message size into much smaller size. So that's the whole point of the hashes. If you remember that usually the input size is significantly larger than the output size. For example, a megabytes of data could be translated into 32 bytes of data. Okay, so hash values could be any number between 0 to the 2 power of 32. 2 to the power of 256, because this is bytes. The important part of a secure hash function was collision resistance. If you remember, we defined collision that if you have a hash function from M to T, we said that we find a collision if we find a pair X and Y that are not equal to each other. Both of them are member of the message domain M, such that the hash of X is equal to hash of Y. So if I can find two pairs, any two pairs in my message domain that results into the same hash, we say that we found a collision of this hash function. And of course, given that M is much, much larger than T, of course, there will be much collision. So there are collisions. The whole thing about secure hash function is that it's hard to find these collisions, but there exist collisions in hash functions. So just keep that in mind. So it's not like impossible for some to find a collision. But when we say a collision resistant a hash function, the formal definition of it is that we say that an function H is a collision resistant hash function if it's hard to find even a single collision. So any two pairs, it would be very, very, very hard to say. So in other words, we're going to say that H is a collision resistant function, or a CRF. Okay. And when we say hard, if you remember back in the day when we were talking about hardness was kind of like a relative concept. We usually say hard is something that takes a lot of time to solve, right? So for example, probability in semantic segmentation was that it was smaller than some epsilon. And we said that epsilon is a parameter that we decide, for example, 2 to the power of 256 or something. So when we say hard, it means that, based on some definition. And examples of secure hash function is secure hash function algorithm, or SHA, which depending on the size, you have different types of SHA. Like you have SHA-256, you have SHA-384, and so on and so forth. For example, SHA-256 is a function X that size of X is less than 256 bits or 64 bytes. 32 bytes. Okay. So how do we use hash functions in the context of blockchain? The hash function is used for what we call committing. Okay, so essentially when we are committing something to the blockchain, it means that we compute the hash and send the hash of that value to the blockchain. Okay, so for example, let's say Alice has a large file M and she wants to post this file to the blockchain, because the whole point of blockchains, if you remember, is that we want to kind of store some transactions, right? So instead of sending all those data, what she can do is that she sends the hash of that data, which much, much smaller. And then the nice thing about this is that, once, if you want to kind of, check the commitment, then the other user, Bob, can read H, and then later she can find M prime, such that H of M prime is H. So in other words, given that H is a collision resistant function, the only way that Alice can prove that this message is indeed the same is that she can send the hash function of her value to the blockchain. Later on, if somebody wants to inspect and check whether this indeed is the message, all she needs to do is providing the message, right? If she can provide the message, then anybody can verify whether this message is the same message at the commitment time. right? The reason for that is it's hard to find another M that has the same message. That has the same hash. Okay, so let's say let's go over it one more time. Let's say I have a number. Let's say I have 1,000. I have a message like hello, this is Nader, right? So what I can do is that I compute the hash of hello, this is Nader, and send the hash to everybody. Okay, so I'm sending the hash of my message to you guys, and you store my hash. Okay, if like 1 year from now you want to see what was the message, you can always come back to me and say, provide me the message. Okay, and I'll provide you my hello, this is Nader message to you. And in order to verify that this is indeed the same message that I sent you last year, you can compute the hash of this new message that I provide to you and see whether this hash and the other hash is the same thing. If they're the same thing, then you're reasonably confident that these are the same messages. The reason that this works is I cannot find two messages that has the same hash function. If I could, then I commit one message. Next time you ask me, I'll provide the other message, right? But the whole thing about CRF is that I told you that it's very, very hard to find two pair of messages that has the same hash function, okay? If I can magically do that, then I can lie as much as I want. I can always commit a hash function. Later on, I can lie about that hash function, okay? So this is why we call this hash function a binding commitment, because as soon as I provide H, I'm kind of committed to bind it to the message M, okay? But again, the security of this system is relying on this fact that it's hard to find another message M prime that has the same hash. If somebody can break that, they can break this commit. Does that make sense? Yeah.
If it's like the verifier gets the message, then what's the point of doing the hash? Because now they know what your message was, right?
So see here, nothing is confidential, okay? So we're not trying to provide confidentiality in this. We just want to verify that this transaction happens, right? So the whole point is that instead of like storing all the transactions, you're just storing the hash of transactions. And whenever we need to verify a transaction, we can always ask for the transaction and verify that this is indeed true, right? Think about it as like storing some receipts. And then whenever somebody asks you, provide these receipts to them, right? So this hashing function provides you this capability of doing this. And the nice thing about instead of storing the actual message, like storing the hash, is that hash significantly smaller, right? So alternatively, I could have just stored all the messages and say, okay, these are the messages. Everybody store this. Every transaction, this is everything you need. So this would be not scalable, right? So instead, we compute the hashes and commit the hashes, and on the blockchain, we just store the hashes. We never store the actual transactions. Cool. And so this is what we call committing to a blockchain. And then usually we're committing to a list, okay? So think about this as like, S as a list of multiple messages. What we can do is that instead of, like, as I said, sending all these messages, Alice only commits the hash function of the entire list. Similar things that you did for your attestation, right? So you only store one final hash of the entire memory. You don't like compute the hashes of every line. You don't store the entire memory. Just compute one hash of the entire thing, which is kind of concatenation of all of them together, okay? And then the big thing about this is that this is a short binding kind of commit, okay? So I'm only storing this H. And then in order to kind of later on check whether this message is really the message that, Alice, for example, committed, we're going to use this verification function that takes this H and takes another thing that we call proof, that I'm going to describe what it is. And then they can verify whether this indeed is the same hash or not. If this is the same hash, it means that the message was accepted, okay? And again, the security of this is relying on this fact that the adversary cannot find a message such that it's not similar to S, it's not equal to S, but has the same hash, okay? This is hard to find, okay? So how do we actually kind of like commit this, and what's this PI? This is based on this thing called Merkle trees. Yeah, question?
What's the question? What's the bias of I?
I'm gonna describe what is a pile. Yeah. Other questions? Okay, so in order to understand what is a pi of I, you have to understand what is a Merkle tree. Any of you know what is a Merkle tree? Okay, so Merkle tree is this, is as the name suggests, it's a tree. Okay, so the idea is that if I have lots of messages like this, in order to store these messages, I can you can design this in some form of a tree structure that I'm going to describe, and I can only kind of like store the root of this tree, which is the hash of the root of this tree, and then I can later on prove that indeed mi of all the messages within SI, I can prove that this indeed part of this list. Okay, that's what I want to store. And the reason that I wanted to do it this way, because regardless of the size, I can always store just one hash, and that's really nice. Okay, so how do we do this? We kind of store this in this format, that we have all the messages in my leaf in the lowest level of my tree. Then what I'm gonna store is basically I'm gonna store the hash of each of these messages at this leaf. Okay, so these messages are essentially the hash of these leaves. Then what I'm going to do is that I'm going to pair them up and compute the hash of that pair. So essentially y1 is hash of m1 and m2, y2 is the hash of m3 and m4, and so on and so forth. And then I kind of keep repeating this until I reach to just one entry to the root of my tree. So I hash y1 and y2, get y5. Same thing on the right side, I get y6. I hash y5 and y6, and eventually I get one hash function, one final hash value, which we call it h. Okay, so in order to now, for example, prove that m4 was indeed part of this list, okay, so for example, someone wants to prove that m4 was one of the things that was part of this, then we're going to provide this proof called M3, Y1, and Y6, okay? So this is the proof that we're going to provide. So what we're going to do is essentially we're going to do this. So Alice wants to prove that M4 was part of this blockchain. What she does is that she provide M4, M3, Y1, and Y6 to Bob and say that, okay, these are the values. And now go figure, see that whether I'm lying or not lying, okay? Bob, what Bob going to do is that he's gonna compute the hash of m3 and m4, and he's gonna get y2. Then he already got y1 from Alice. He's gonna then compute the hash of y1 and y2 and get y5. Also, the proof already gave Bob y6. Bob gonna continue computing the hash of y5 and y6 and gonna get h prime, which is the root of this tree. Then he's gonna check h prime with the value that is already stored in the blockchain, which is h. If h prime and h is the same thing, it means that Alice did not lie. In fact, M4 was part of this blockchain. Okay, so the nice thing about this is that instead of I can verify all of these messages by just verifying log n of this tree. Okay, I don't need to do linear. I just do log n of this tree, and I can verify any message that I want. Okay, so the whole point of having a Merkle tree instead of just doing hash of everything and save hash of all of them is that verification is much more faster and much more efficient. And also, I can only need to store this in my blockchain. This is the only thing that everybody needs to know. Everything else, if I want to check, I can always ask for the proof. You provide the proof, you provide the message, I can independently verify and check whether this indeed is correct or not. Okay? Make sense? Questions? Yeah.
So then the proof is really just the set M3 Y1 Y6.
Exactly.
And you could act on the tree.
Yeah.
The tree is public.
No, you don't need to know the tree. Alice knows the tree. Alice provides this. H is public. This is public.
H is public.
Yes.
Then how do you follow through with these hashes? Are you assuming that those hashes are somehow special? Because I'm thinking if you pre-compute M3 such as this collision, then when you combine the hashes, it would give you an incredible.
Yes, of course. If you can find it, so the whole point of here is that I can find a collision in any of these, right? If the adversary can find a collision in any of these three things, then it can lie about M4, right? But if you remember, we said that hash function is collision resistant, which means that I cannot find any two pair that has the same hash, okay? So if I cannot find any two pair that has the same hash, I cannot lie in any of these three steps. Make sense?
So the hash is like strong enough where you can't pre-compute, because I thought SHA-256 you can still pre-compute given enough time, it just takes a while.
What do you mean by pre-compute?
Say you have like M3
Mm-hmm.
and you have M3 prime, and they both collide to the same hash when hashed with M4.
Oh yeah, so of course, as I said, every hash function you can eventually find a hash that has the same value. It just takes a lot of time.
Okay.
That's the difference.
So Bitcoin or whatever blockchain, the hash is just like, the hash function collision is just so astronomical.
It's just so long time. That's why even like verification of things is not that easy. Like finding a specific hash is not that easy. It takes a while. So let it be that finding a specific hash of this. Like a simpler problem is much harder than you think than even finding this collision. But yeah, so these are very large. So it's kind of like telling you that find two numbers that has the same output in 256 bits, right? This is how, and then there are proof that is, so there are algorithms for hash, there are attacks for hash. All of them has a complexity. And people have shown that like it takes 100-something years with current computers to find a collision.
Gotcha, okay.
All right, so I talked about Merkle trees. So essentially the theorem here is that given n, if h is a CRF, this is the important part, that we need to find an h that is collision resistant function, then the adversary cannot find a tree or a list of size n such that the message is not one of the messages is not part of that S. Okay. And in other words, then all we need to do is just commit S. In other words, just compute the root of this hash and store that. And we can always provide the proof, the message, the I and the H, and then we can easily verify that whether or not this list is indeed a list. And then there are proof for this. I'm not going to go through this. But what is this? Why this is a useful thing to do? Because essentially all I need to do for transaction list S is that I just need to store the root of this tree. I don't need to store anything else. And I have this method to kind of prove every single message in this system if I want. Yeah.
So I guess kind of to jump off, like if you're just storing the loop,
Mhm.
where's like all the messages and like the rest of the tree being stored? Because you want to verify, like where does that come from?
Yeah, so you can always like, so usually blockchains has this thing called header, and then there has this body. You can store in the body as much as you can, and this depends on the protocol. So you can, for example, store the body, like you can, all the transactions you can store in the body. You just store them in plain text, okay? So now the idea is that how can I make sure that this thing cannot be changed, right? Remember, we want to have what we call an append-only data structure that is hard to remove. Okay, so this is like the way that you kind of like, you have the log of all the transactions, like you have all the messages there, but this H is providing you this guarantee that you cannot change those logs. If you do change those logs, your H will be different and you cannot lie about it. Does that make sense? I mean, what you're really storing is really depends on what is the application. If it's a Bitcoin, for example, could be all the transactions. They usually have like specific kind of method for storing this. In your project, you're going to see that, for example, we have like a block size of like saying something, and then we're going to compute the hash of that. So you see an example of it in your project. So so this is the part that was blocked, okay? So each block is something like this. It has a header that has this H, and then it has this data. Then we need to chain these things. How do we chain them? So we chain them using this technique that we hash the block header and store it into the next chain, okay? So if usually we start with what we call a genesis block, the first block, but other blocks always store the hash of the previous block, the Merkle roots, and then all other data that we have. Okay, and then we keep continuing doing this. If you want to add a new block, all you need to do is compute the hash of the previous block, and then have the roots of the new transaction, the hash of this new transaction, and then any other data, any metadata that you want to have in your system. And then you can add as many of these blocks to your system. And then if anybody change anything in any of these parts, in any of these blocks, everything will basically mess up. Again, in your project, you're going to see that we have a big Excel sheet that you have to add things to it. And if you want to mess up with it, you can change one of the things in like earlier blocks, and you see that everything will be basically messed up. This is how we kind of make sure that the blockchain is not changed. Yes.
Who gets to choose like what the next block is going to be? Nothing centralized about it, and like different people.
So this is where the miners will fight. So like request comes. So for example, let's say a new transaction needs to be happen, right? So I need to put this into a new block. Okay, so someone needs to compute the hash, okay, and then put it into a new block. Multiple miners might compete for this, so we need to have a mechanism to select which miner should do the computation. That's where all these consensus layer things comes into the play that I didn't talk about. So there is like algorithm of how to choose the miner, how to actually kind of tell everybody that, oh, the block has been updated and so on. So there are a whole bunch of these consensus layer that needs to be happen.
So if you like buy something with Bitcoin or whatever, like everyone sees that and then everyone like starts fighting over who gets to add that. The best gets the
Yeah. Yes, exactly. And then there is also always like this equitables, make it more fair and so on and so forth that exists in these systems. So this is where it becomes blockchains. The last part is actually proof of work. So the proof of work is that, so we want to have this objective that it should be hard you should take some time to solve a problem. In order to make this process of mining fair, you don't say that, okay, any hash value should be, for example, acceptable. I want a particular hash for this function that if I compute that hash, so I want to have this function that instead of like originally I have h of x, okay? And then h of x was just one final hash value h, okay? Now what I'm telling you is that instead of doing h of x, let's do h of x and y, okay? Usually this y is we call it nonce or salt, depending on the description. And I want to create this h of x and y and create this h prime, okay? So now if I change y, the h prime will be different, okay? So now what I can do is that I can say that I'm looking for a particular puzzle in this h prime. So find the y. So for given x, by the way is that s that we had before, right? So x was something that is given by the transaction. You cannot change x, but you have degree of freedom in y. You can play with y. Okay, let's say we call this y the nuts. Okay, so you can play with this nuts, but we ask you to choose this y such that this h of x and y has a certain property. Okay, formally this property should be, for example, it belongs to a small set. So for example, in your project, we're going to ask you that find this y such that given x and y, your hash starts with 4 zeros at the beginning. Okay, this is the puzzle that you need to solve. Okay, so you kind of need to iterate over y, compute h of x and y such that your hash value starts with 4 zeros at the beginning. Okay, for real Bitcoin, this is actually much bigger number. But for your class, you will see that actually 4 actually takes quite some time. If you actually make it 5, most of your program's not going to finish in 2 to 3 days. Okay, so this is what we call proof of work, that the miner can prove that they can indeed do this mining job properly, and this is one way of kind of like making sure that who can solve this puzzle as fast as possible gets to get the incentive, which is kind of like some Bitcoin or something. Okay, and as I said, this puzzle, any arbitrary puzzle, for example, in your project, you're going to see like starting with 4 zeros, just an arbitrary number. But in Bitcoin, for example, this is different. This is what we call proof of work. And it's kind of like wasting resources a little bit, because essentially you need to kind of solve this arbitrary puzzle in order to kind of prove yourself that you did something. That's why there's another thing called proof of stake that is kind of a little bit better, a little bit less computationally heavy. But most of the Bitcoin systems actually these days are, like Bitcoin specifically, still use proof of work. And that's why mining takes essentially what your miner does really most of the time is just trying to find this hash. It's just iterating through different values of nuns in order to find a hash that satisfies the requirement. Okay, that's really what it does. Make sense? So yeah, so for example, for Bitcoin, the hash is SHA to double hash function. And then of course you can always parallelize this. You can have multiple computers, you can have massive GPUs and all those things to solve this problem. And if you can do it, then you can solve this puzzle. Okay. But there are theorems that, for example, if H is indeed a random function, then the best algorithm that requires the best algorithm possible to solve this puzzle requires the evaluation of H. Okay, so you can kind of know that how difficult your puzzle should be in order to make it, reasonable. And again, for different algorithms, including Bitcoin, this changes and so on and so forth. Again, I'm not going to really go to the details of each of these algorithms. Okay. Any questions so far? Yeah.
I had a quick question, which is, so we've talked about how it's quite difficult to find a message that would collide hash. My question is, if for a quantum computer, would it be easy for it to find the collision, or would it be equally tough?
For current SHA-256, it's equally tough. I think it's slightly easier depending on the hash function. For example, for AES-based hash functions is half the size. So for example, if you use 256, it becomes 128. So if, for example, 256 takes n time, then 128 might be n divided by 2. So it's something to consider. But hash functions still remains fairly secure for quantums. Yeah. And then the last thing I want to talk about blockchain is, of course, who is authorized to do different things. And this is where you can always have your digital signatures. If you remember about digital signatures was, you use your private key to sign and use public key to verify. So in order to make sure that not everybody can do things, or at least verify who did what, you can always use public and private keys. And again, just a quick reminder, what again useful for quiz as well. Digital signature scheme is a triple of algorithm of gen, sign, and verify. Gen creates the key pair, the public and secret. Sign is the one that takes the secret key and the message and output something like delta or signature. Verify takes public key, the message, and the signature, and verify that this indeed is an acceptable signature or not. And a secure informal description of secure signature is that adversaries who see many messages still cannot forge a signature on a new message. If this is the case, we say that this is a secure digital signature. There are a whole bunch of different signatures. There's RSA signatures that are not used in blockchains. The blockchains actually use what we call the electric curve digital signatures algorithms, ECDCA, which use smaller signatures of like 48 to 64 bytes. There are a whole bunch of others. There's also post-quantum signatures that's being used these days. Signature parts is vulnerable to post-quantum, so we have to be careful about that. And yeah, so there is also other signatures if you're interested. So that's what we're going to do in order to kind of see who did the transaction, verify that the person who sent the transaction is indeed the person that claimed that they're sending a transaction. That part is when we are using the digital signature. So in order to kind of create an account, you always have to have like a secret and private. So what are the other important concepts? As I said, selecting the miner, proof of work, how does the consensus algorithm works, different types of attacks to this blockchain. These are all interesting questions in blockchains. Fortunately, we don't have time to go over them, but just keep in mind there are lots of interesting questions. In your projects, you're going to do just a very simple proof of work plus some creation of blockchains. We're not going to do the verification part. We're just going to create a new block and add it to the system using the proof of work. That's would be what we're going to do. And then our system going to be like basically an Excel sheet that everybody sees. The assumption is that everybody has a copy of that Excel sheet essentially. And then we're going to create some transactions, and then we're going to create the blocks. And you guys needs to create a blockchain. So essentially, the goal of the project is that everybody has to create their own block and add it to the system. And you will see that at the end of the kind of once everybody adds theirs, you will see actually a chain block that if somebody change anything at the beginning, will mess up the entire thing all the way through to the end. Okay. Any questions? Yeah.
So for that, like, CA5, that's gonna be like a class wide, there's gonna be like a class wide blockchain?
Yes.
Oh,
All right. So let's have a quick break, and then we're going to talk about other things. So let me actually, as you guys asked for it, let me quickly talk about a few other things in cryptography, which is interesting. Of course, there is a whole bunch of like post-quantum cryptography, which is kind of like, you know, a hot topic. What I'm going to talk about is like a slightly different thing that is also very interesting. I'm particularly doing some research on this, so I wanted to share with you. But part of it is actually relevant to quantum computing as well. So the problem that people are interested in, I'm going to talk about is, can I compute a function without revealing its input? Okay. In other words, that if I have a server, okay, that has a function f, can I find, let's say I want to compute f of x to y. On the cloud side, can I have the f, but never seeing x, instead seeing x prime, which is, let's say, for example, the encrypted or whatever version of x, and still provide y? Okay. And this is actually an old problem and very useful problem. To kind of give you why this is a useful problem, let's actually give you an example. And this is a very old problem called millionaire's problem. So the millionaire's problem is this, that let's say Alice and Bob are millionaires, okay? And they want to see which one of them has more money, which one is more wealthy. But the catch is they don't want to share how much money they have. They just want to know and find this binary answer that whether x is greater than y, or whether x is equal to y, or whether y is greater than x. Okay, so this is the answer, the question that we want to answer. And of course, the simple answer for this is both x and y tell some trusted third party about their wealth. So for example, me and Jeff Bezos are millionaires and billionaires, and we want to see who has more money. So we talk, we tell him to like, this is the money that I have. I say it privately. Jeff Bezos also kind of call him and say that this is the amount of money that I have, and he will announce who has more money. Okay, without really revealing our money. Okay. So these kind of types of problems are what we call privacy preserving problems, which the idea is that can I evaluate a function without really revealing the values, and nobody knows the values. Okay. In the case of trusted third party, the trusted third party will know the values, but we want to see whether I can solve this problem without the existence of a trusted third party. So me and just Jeff Bezos can fix this problem. We can settle this problem among ourselves. Okay. And there are a whole bunch of solutions for this. There's what we call multi-party computation. There is what we call a homomorphic encryption, a method. There's secret sharing. There's hardware-based. There's also non-cryptography-based. Very interesting problem that people solve it. So as I said, there is a trivial solution, and that is that if there is a trusted third party, then I can always share this values with them. But the problem with this privacy preserving is there is no trusted third party. So again, this is a decentralized problem that we need to solve. Okay. So the first question is that, do you think encryption will help in this case? Why encryption doesn't help? Anybody? it seems that we already solved this problem with encryption, but do you think encryption is actually applicable here?
Encryption like holds some of the same properties as the original data.
Mm-hmm.
Your information on the data,
Mm-hmm.
revealing X, Y,
Mm-hmm.
it still holds those properties.
Yes, exactly. And do you think do you know what are those properties? Okay, so yeah, so first encryption cannot help. The reason that it doesn't help is that encryption in general helps you with data at rest. That's if you do computation, you cannot compute over encrypted data, right? What you can is that you have to decrypt things, compute them, and then recrypt or encrypt them again, and then well, basically transaction, and when the data is what we call at rest, you can provide confidentiality. But when you actually want to add two numbers together, you cannot add the encrypted version of two numbers, okay? In fact, what I want to do is exactly this, that I want to have a capability that do computation over encryption, okay? So let's say I have message 1 and 2. What I want to do is having a method that I can, for example, do M encrypted version C1, M2 encrypted version C2, and then I do mathematical operations on this here, and then I get a value, let's say Y, and then if I decrypt this value, it's as if I do operations on M1 and M2. And in fact, the operations that we are really interested in is addition and multiplication. If you do addition and multiplication, then you can essentially do any polynomial functionality in the system, okay? So most cases, if I can add two numbers, and this number is as if I added M1 and M2, and then if I can multiply two numbers, decrypt it, and it's as if I multiply these two numbers, then I'm good to go with any polynomial function. And this essentially I can do any linear operations. For nonlinears, the story is a little bit different, but for linear operations, I can do this and I'm happy. Okay, so essentially the idea is that can I find a mechanism to encrypt M and M1 and M2 to C1 and C2 such that then I can just operate things on C1 and C2, get the final value, decrypt the final value, and magically have the final value of as if I did it on my messages, okay? This is what we call homomorphic encryption, okay? So essentially the idea is that I'm going to have this F function that is evaluated on the server, and the server never sees what X is. It always sees C, which is the encrypted version of X. Yes?
It's not a naive question, but then why not just have like a set of monotonic functions and then to solve the millionaire problem, you just randomly take one of those monotonic functions, apply them to the inputs, you get your outputs, you can compare the outputs, and you won't know which function you use.
Yeah, so you can, for example, like you were saying, like add it. So basically you were saying that let's say I have M1 and M2. What I do is that I add one R and then another R, R1 and R2, and then I compare M1 plus R1 and M2 plus R2. Is that what you're asking?
Something like that, or just take like any monotonic function like squaring or cubing.
Yeah, as long as they are not, yes, that's what we call secret sharing essentially. So you can actually add secret shares to the numbers and then compare that numbers together, and then, but then the question is who adds. So if it's a two-party problem, so how do you who is gonna evaluate this monotonic function? Right? Because for example, if me has this function, I'm going to add an R, and then I can just add a very big R, right, to my data, and then send it to you, and then you have to apply the same thing to yours. So who's gonna do what? So for a two-party problem, that would be very hard. But we're gonna give you actually a solution, so don't worry. But before that, let's actually talk about how encryption could help. Because, for example, a solution to this problem that I said is if I can do, instead of doing operation on M1, if I can do operation on C1, then I can send my C1 to you, and then you can do all operations and send me back the results, right? That's what I want to do. So this is what we call a homomorphic encryption mechanisms, HE. Think about HE as anything it's other similar to what we have learned in the class, like AES and RSA and so on. homomorphic encryption was like something that people looked at it for the longest time, but it's really the breakthrough happens in 2009. It's a different time in 2009. It wasn't the same time that Satoshi created the blockchain. This is done by this guy called Greg Gentry, who actually kind of made this breakthrough that I'm not gonna talk about, but homomorphic encryption since then has been used a lot, and homomorphic encryption itself could be a symmetric or asymmetric mechanism. So both of them exist in the literature. So as I said, the goal of homomorphic encryption is evaluating any polynomial functions without revealing the inputs. And as I said, essentially for this, I need only addition and multiplication, okay? And then for X and Y, as I said, I need to add them in the encrypted version, decrypt them, and get the same value as if I added those two numbers, and same for multiplication. A simple example of this would be something like this, that let's say I have X, I can basically kind of like multiply X to 2 as somebody says, and then if I also have Y, I can do the same. Then I can add these two numbers, let's say 3 and 5. Then I can add 6 and 10. I add these together, I get 16. I just divide it by 4, and then I'll get, I divide it by 2, and I'll get 8. And then if you actually check, you will see that if I added 3 and 5, I would have got 8, right? So essentially the encryption in this case is multiplying things by 2, and the decryption version was dividing it by 2. Okay, so very simple and straightforward. You can do the same thing with actually for multiplication as well. If I multiply this by 2, I get 6. Multiply this by 2, I get 10. Multiply these things, I get 60. And then in order to go back to that, I do 2 and 2 because the multiplication, essentially the decryption function is slightly different. It's 2 times divided by 4, I get 15. And if I actually multiply this, I'll also get 15, right? So it works. Yeah, you can do these things. But is it secure? Of course not, because essentially, remember, for security, I need semantic security. I need to be able to do, if it does this twice, nobody can knows about this. And it shouldn't be linear and all those things. So all those things that we learned in the class for AES applies here as well. It shouldn't be easy for the adversary to decrypt these things. It should be completely uniform and all those things. For example, multiplied by 2 is a bad idea because you always have only even numbers, never odd numbers, and so on, right? But generally, to give you an idea that how this would work is something like this could work. Yeah.
Could you then do like a sum of like linear operations?
Yeah, you can repeat this as many times as you want, right? Because as long as I know how many operations I did, I can always just revert it back.
But it's still not secure.
It's still not secure because essentially, I mean, the security should be just by seeing this, I should not be able to reveal what is 3, right? So by seeing 6, I should not be able to say this was 3, right? That's the same thing that we had for AES and so on.
But like if you have a set of unknown like linear operations, it'd be difficult to work back.
Yes, if you add them together and say, okay, now I only see sum, but remember, you don't see just the sum, you will see also individual numbers. The server will see individual encrypted versions and the operation, right? So how we can actually improve this, there are a whole bunch of solutions for this. So there's just not one homomorphic encryptions. There's actually, this is, as I said, a very active area of research where lots of interesting solutions. One that is particularly interested is what we call learning with error problem. So essentially learning with error problem is that, can I solve this equation like this? That I have a bunch of different kind of variable, S1 to S4. I have a bunch of equations. I want to, for example, find S1, S2, S3, S4, such that it satisfies all these equations at the same time. We call this LWE problem. It's actually useful for many other things. But what is going to be used for homomorphic encryption is that my homomorphic encryption mechanism would be something like this, which essentially I have this A and S and E and Q, and these are the parameters of my my homomorphic encryption mechanism. So we usually call this parameter size N. This Q is the modulo. This E is what we call an error, E. And then the error should be kind of uniformly distributed over this ZQ, this modulus Q. So essentially the error could be any number between 0 to Q. Then we need to choose a random number A uniformly from a distribution of ZQ to N. And then also, as I said, E has to be randomly chosen from ZQ. And this would be your kind of algorithm to kind of encrypt things. You do AS plus E mod Q, and this would be basically your encryption. Decryption would be exactly the same thing on the reverse order. Why would this work? Think about this way, okay? So this is how we're gonna, for example, encrypt things, okay? So my secret key is P, okay? My message is B, and for now, assume that message is just 1 bit, either 0 or 1, okay? So here's how I'm gonna encrypt things. I'm gonna do A times B plus 2R plus B, okay? And then, for example, if I have two messages, like let's say B1 and B2, I'm gonna get A1P 2R1 B1, and then here I'm gonna do A2P plus 2R2 and then B2. Okay, so if I add these two numbers together, what I'm gonna get is that I'm gonna actually kind of simplify this quickly. So what you're gonna see is that you're gonna see A1 plus A2 times P plus 2 times R1 plus R2 plus B1 plus B2, okay? So you're gonna see something like this. That actually looks very similar to another A prime R B. And then this is exactly what you want to get if you decrypt this, because the decryption process of this is essentially like this, that I'm gonna do modulo P first to get rid of this. Then I'm gonna do mod 2 to get rid of this, and what are going to remain is B. So the decryption process is mod P mod R, and then I'm going to get my B. And then if I do mod P mod R here, I'm going to get exactly the same thing. Mod P will get rid of this part, and mod 2 get rid of this part, because this is always like, you know, a multiple of 2. What I'm going to get is B1 plus B2. And then you can verify that, you know, if you multiply it, you're going to get exactly the same thing. What you're going to get is a little bit more terms here, but eventually all of them would be 2 times some things. And then here you're going to get A1, A2 times P. And again, if you do mod P, mod 2, you're going to get rid of both, and you're going to get B1, B2, or B1 times B2. Okay, so this would be a very, very simple homomorphic encryption mechanism, which is indeed secure. If you think about how this really works, it's essentially what we are doing is that if my point was essentially B0 or 1, so essentially my point was used to be here, either 1 or 2, I'm going to expand this into the P domain, okay? So essentially now my point is that instead of being 0 and 1, it's in the lattice of a lattice of P, okay? So it's P, 2P, 3P, and so on. But then I'm going to add noise to this, right? So I'm going to add this 2R plus B noise. And as long as this P is much, much larger than B, then essentially my points would be anywhere in this neighborhood, right? So between these two. And that's why when I do mod P, I'm going to basically move this to between 0 and 1. When I get rid of the noise, then I'm going to basically do this either 1 or either 0, right? This is really like visually, if you think about how this would work, is that I'm going to expand this into the domain of P. Then I'm going to move this a little bit to the left or a little bit to the right by adding the noise. And the thing that the adversary doesn't understand what this message is, because it cannot find where in this point this noise is. Because if the adversary can find the exact noise, then they can find B. But noise could be any number between P and 2P, or NP and N plus 1P. And then as long as this P is large enough, these are many, many, many numbers. Okay, this is how this basically works. Questions? So yeah, so as I said, decryption is essentially C mod P mod 2. Essentially, I'm moving back this to, so first of all, I'm moving back this between 0 and 1. Then I'm moving back this to either 1 or either 0 or either 1 by removing the 2. Okay. The biggest problem with homomorphic encryption is the issue of noise. Because essentially, I'm gonna skip these things, but you can, as I said, you can always do addition and multiplication. I did the addition for you. You can do the multiplication yourself. The problem with the noise is that the noise should be smaller than half, right? Because if it's bigger than half, it's going to roll over one step higher or roll over one step lower, right? And if you think about this addition and multiplication, actually, if I go back, you will see that my addition, what would happen is that my new R was actually R1 plus R2, which means that each addition increased the noise by that factor, right? So if I do 2 additions, I'm adding 2 small noises. If I do 100 additions, I'm kind of increasing the amount of noise by a factor of 100. And as I told you, I need the amount of noise space that I have is half of this space. Okay, so for example, if P is number equal to 1,000, I only have 500 as kind of my wiggle room. Like I can only add 500. And then let's say if my noise is initially 3, then it means that I can do at most like 150 something additions. I cannot do more than that. All right. So this is a big problem with homomorphic encryption, that since I'm actually doing all the computation with noise, the noise grows, and at some points the noise would be so much that I cannot recover my message. Okay, so this is what we say the noise problem in homomorphic encryption. There are 2 solutions for it. One solution is what we call level homomorphic, which means that we already pre-compute how much noise we can add to the system. Okay, say that, for example, this system, you can only add 100 numbers. More than 100, you cannot do this. Okay, so as long as you can do 100, you're safe. The second thing that you can do is what we call fully homomorphic encryption, or FHE. The idea of FHE is that once we reach that 100, we have to kind of decrypt and re-encrypt again. Okay, and this decrypt re-encryption is actually also done homomorphically. So the beauty of homomorphic encryption is that all the operation, including the encryption, decryption, can done homomorphically. In other words, I can keep repeating encryption, decryptions to reset my nodes myself. So essentially, if I have one key to kind of do the computation, if my noise grows, at this point, I can use another key to kind of encrypt this again. This is another function that I do. And now I have fresh set of noise to do this. So, and I can do this infinitely, right? I can, whenever my noise kind of grows, I kind of like switch this to another encryption key, and then I keep doing this over and over again. Of course, the overhead of this method is that every time I do this, I essentially do another encryption, which is very time consuming and very energy inefficient and so on and so forth. But in theory, I can do infinite amount of computation. Just this is what happens in 2009, actually. Questions? So as I said, level homomorphic or fully homomorphic, and this process we call bootstrapping. So when you actually re-encrypt the system with a new key, you're doing what we call a bootstrap. Okay. So why LWE problem is hard? Because LWE's problem is based on hardness of lattices. Essentially, what we are really doing is we have the lattices. First of all, is a ND dimension of points of any point. So, for example, X and Y is a lattice if there's any points that you can show it with 2 bases. So, for example, let's say my basis is this. So essentially, any point that I can create with this basis would be part of this lattice. So, for example, this point would be 3 times of this plus 2 times of this, right? So this would be part of my lattice. Essentially, creating any points in this ND domain based on this base vectors would be part of the lattice. Okay. So why this LW is a hard problem? Because the LW is kind of reduced to this problem called closest vector problem in lattices. Okay, so for example, let's say all of these black points you have are lattice points in your lattice. Okay, and then let's say your basis is this B1 and B2. Okay, let's say now I want to find this green point. So I want to find the closest vector to this green point, or closest lattice point in this lattice to this green point. In this case, is this red. Okay, so out of these kind of 4 by 3, 12 points, this green, this red one is the closest to this green. Okay, but if this is an n-dimensional problem and I don't know the basis, finding where this point is closest to is a hard problem. There's actually solutions for that. This is actually reduced to some other, NP hard problems. Those of you who took in algorithms, have you ever seen this closest vector problem in your? How many of you have taken algorithm course? Have you seen closest vector problem before? Interesting. UCLA is not teaching. Anyway, so it's closest vector problem is actually like one of the very kind of 101 problem. Have you seen knapsack problem? Okay, good. So just like, closest vector is like very kind of like also like close to that kind of those range of problems. So finding the closest vector in a lattice is a hard problem, trust me. Just Google it and you will see some discussions about it. So what will happen is that this learning with error will reduce to the closest vector problem, because this, again, like very intuitively, these 2 points and this essentially this noise that we added, I need to find whether this is closer to here or here, and it's hard to find that. Just trust me that this is hard. And this is why this is a problem that's very interesting, and people can actually build crypto system based on that. This is different than, for example, RSA problem, which was factorization of prime numbers. This is a different ways of creating this. The nice thing about lattices is that these are quantum safe algorithms, actually. Like quantum computing cannot solve this shortest vector problems either. And that's why many of these post-quantum crypto algorithms are actually based on LWE and lattices in general. Okay, so just keep that in mind as well. So what is the main challenge in homomorphic encryption? The main challenge in homomorphic encryption is actually the performance. All these things that we are adding to the system, adding noise and multiplying things with AP and all those things, it just bloats the system up, okay? Because essentially what used to be, for example, an 8-bit data is going to be like 256-bit data, okay? Just the same message increases significantly. In AES and all those things, we didn't have this problem. The message size stayed the same, but in homomorphic encryption, your encrypted version of your data, your ciphertext, is actually growing significantly. And what used to be an 8 by 8 bits, for example, multiplication, is now 256 bit by 256. So you can easily see how these things kind of blow up significantly, right? So this is the issue of homomorphic encryption. It's unfortunately order of magnitude slower computation systems. And then the second problem is nonlinear operations. So far, I just show you how you do multiplication additions, but if you do comparison, anything like that, it's not going to happen in homomorphic encryption. There are solutions for it, things like approximate computing, hardware accelerators for homomorphic encryption, and so on. This is actually research that's being done. My group is actually working on these things as well. So just to recap, remember we want to solve the millionaires problem, and one of the ways of doing this would be something like this. Essentially, you encrypt it and apply something like subtract and see what's subtract is equal to 0 or not. Something like that you can do easily to see if you have more money. Another way of doing this is what we call multi-party computation. If you have only 2 parties and you don't want to use encryption, you're going to use what we call a Yao-Garble circuits algorithms. I don't think we have time to go over it, but maybe just take a look at the slides to see if you can take something out of it. Essentially, the idea is that GC algorithms or Garble circuit algorithms is trying to evaluate any gate. So for example, let's say an AND gate, okay? So let's say I have G and E, these 2 inputs. I don't want to reveal the inputs, but I want to compute the AND gates of those 2 inputs, okay? And GC actually provide a method for this. Let's say Genie and Even are the 2 players. Genie has input G, Even has input E. We want to compute this without really revealing what is G and E. So none of them actually have both numbers. Everyone has just one number. Similar things to the wealth problem, right? So you can reduce the wealth problem to this problem very easily. So GC actually provides a solution for it. The solution is based on what we call the garbling. For example, one of these 2 players becomes the garbler. And then what they do is that they basically create this encrypted version of this. So basically, they create this random, very large vectors and encrypt those vectors using some AES or some encryption mechanism. And then they share it with the other user. The other user kind of do some computation over it, and then they send it back. and then eventually they can actually fix how this problem works. Unfortunately, it's kind of required. Maybe if I finish everything, I'll come back and explain how this works for you. But this basically based on this very, very interesting observation that you can do what we call oblivious transfer, which means that I can transfer something to you without you knowing which one you picked. Okay, it's kind of like, let's say, for example, I put two balls, a red ball and blue ball into a bag. I give you the bag and you pick something without showing to me which one you picked, and then we throw out the bag. Okay, I will never know which one you picked, but you also only see one and only one. You don't see the other. Okay, so this is what we call an oblivious transfer. I transfer something to you. I transfer one of these balls to you. You pick only one of them. You never see the other one. I also didn't know which one you picked. So this is a very interesting and very very cool applications in cryptography. And there's actually, this is the actual algorithms. Read it. If you didn't understand it, you can always ask on campus why I can explain how this works. But it's just magic based on the simple cryptography that we already understand. Okay. So based on that, we can actually solve this GC problem. GC also has, unfortunately, performance issues because there are lots of communication between the two parties, which are actually quite slow. But in fact, you can actually solve the millionaires problem using GC, which is very, very interesting problem. And then the nice thing about GC is that then you can, anything that you can build with gates, which essentially any problems that you have, comparators, adders, multipliers, you can essentially use GC. So you can even apply to nonlinear functions. Okay. And then, of course, you can always do all of these things using trusted execution environments. Now we learn about that. If you remember, the whole point of trusted execution environment was that I don't trust anything but the hardware. I can do the computation. So, for example, solving the millionaires problem can be done on a T as long as I trust the hardware and not trusting the operating system. So just keep that in mind as well. So a little bit of our research. Any questions so far about this? I kind of skipped through the GC part because we didn't have time. But yeah, read it and let me know if you have questions. Cool. So my research is on, of course, on security. My lab's name is SysArc, which is essentially secure systems and architectures. So we do really two things. We do system level research and we do architecture level research. The things that mainly I discussed in this class was more the system level aspects of things, but also work a lot on the computer architecture aspects of things for security. And that's the course I'm teaching next quarter, actually. So if you're interested to learn more about that side, I'd consider taking it. These are kind of like the active projects that we are doing. These three is kind of like the architecture side of things, and these three is IoT side of things. On the IoT side of things, we do lots of side channel for good purposes. I kind of described it a little bit when I was talking about physical side channels in the class. Things like profiling, communication, fingerprinting, localization. And recently, we are getting interested in debugging. So the idea is that you have these side channel signals. They reveal something about your system. Instead of actually using it for adversarial purposes, maybe you can use it for useful purposes. Okay, maybe I can use it in order to understand whether my system has been attacked or not. Maybe I can use it to identify which device I'm talking to. Maybe I can use it to even debug my software and seeing that which part of the software is being run based on these patterns. Okay, given that these patterns are actually data specific, I can actually reveal this information. Okay, so it involves lots of understanding of these signals, some signal processing, machine learning a lot, and understanding of embedded systems in general. That's one thing that we do here. The second thing we do is what we call Internet of Collaborative Things, IOCT. This is also a big project that we are working on. The idea is that, soon we are moving toward this direction that everybody tries to share everything with each other. One can share their sensor to another sensor, one can share their actuator to another actuator, one can share the computation to another computation. So for example, let's say someone comes to your house. What they can do is that they have your cell phone, but they can, for example, offload some of their computation on your GPU machine that you have at home, okay? So this question is that, why do I want to do this? And there are incentives for doing this because things get faster. But the question is, what do I have to give up? And there are two problems that you have to be worried about. One is privacy of your data and your computation, and the second is security. So for example, let's say there are two cars driving next to each other. And very cool thing that could happen is that if these are, for example, autonomous cars, they can share things to each other. They can share their perception to each other. For example, if this one is using a camera or a LiDAR to detect obstacles in front, if it detects anything, it can tell the other one as well, right? So for example, two cars driving like this, there's a blockage in front. The car in behind has no idea, but this car in front can see it. So as long as it sees, tells everyone in the back that, oh, look, there's a blockage, wait, or brake, right? So this would be very nice because it can do what we call multi-layer perception. But what if this front car is an adversarial car? Like, it's just wants to mess up with everyone, right? So it's just say, oh, there's blockage. Everybody brakes, right? So you can quickly break the entire system by just announcing and transferring false information. So now the question is, how can I still use this perception, this shared perception, shared sensing, shared computation without kind of opening this new challenges, this new potential for attacks? This is what we call trusted sensing, trusted actuation, trusted computing in general. How we can actually detect these things and how we can do these things is a very interesting, very challenging problem that we need to solve. And the last thing at the IoT side is that we are looking at machine learning security and privacy. There are a whole bunch of problems with the machine learning side of IoT things that we are interested to work on. This whole concept of privacy preserving that I mentioned, and the whole problem of performance of things like homomorphic encryption and so on, it's actually significantly worse in IoT device with resource constraints. So how can I still use something like homomorphic encryption on an IoT device without really paying a lot of penalties? Is a question that we're trying to answer in our research. And then we're also looking at other aspects of security of machine learning. On the architecture side, if you're interested to learn more, you have to take my class. But essentially, we are looking at things such as how do we build a gigantic chiplet systems and thinking about security of it, how we can make sure that our systems are not really leaking any side channel information, how do I build hardware that doesn't leak, and all those things. These are interests of our work in the architecture domain. And then final things to kind of let you guys go. So essentially, the main message of this course was, we're moving toward the direction of computers becoming more and more, and they are actually controlling many critical systems, right? And as you saw, there are lots of issues with these systems. There are issues at the hardware layer, architecture layer, system layer, even algorithm layer, right? So how do we fix them? How do we make our systems secure? We start with assumptions and protocols and principles, and then everything else was kind of engineering. There was some overheads if you do this. There are some costs if you do that. But if you build them all together, then we can have a secure system. That's really what becomes a computer security research, right? We saw various different things, starting from hardware. We saw there are TPMs, Ts, sensors. Then we talked about things such as secure boots and side channels and faults. Then we talked about things such as attestation, memory safety, and control flow integrity. And then at the system level, we saw end-to-end cyber physical system. We saw problems with the wireless systems and all. So the main thing that you have to understand is that security is a very cross-layer thing. It's not about just one layer. You have to always understand the interactions between these different layers when you're considering security. And hopefully, based on your interest, you can always explore more in each of these layers as you move forward. There are a whole bunch of other topics that we didn't have time to explain. We didn't talk much about hardware security and architecture security. As I said, this is a separate course. But these things that we didn't really talk about: network security, software security, privacy and privacy preserving, and machine learning security. These are very interesting things. There is a course in machine learning security that's going to be taught next quarter. If you're interested, consider taking it with Professor Yuan Tian. There's also a whole bunch of works on network and software security. These are more undergrad courses that you can always consider taking. So if you want to just, increase your knowledge in this domain, I consider considering taking all these courses or just read books and educate yourself. Main takeaways of the course, cybersecurity is one of the key challenges in the modern era. Multiple things that we are seeing. One is that our reliance on computers are increasing. The connectivity and accessibility of these systems are growing, which means that attackers also now, it's more accessible to them. We have been very, very negligent about security for the longest time. Many of our designs have not been secured by design. So there are lots of catch up that we need to make. Unfortunately, we also lacking policies at government level, at companies level. And there are lots of lack of proper education about security. Many people don't know many of these things. And hopefully, at least in this class, we kind of like cover lots of it with educating you guys. And now you become ambassadors of kind of doing this for others when you are joining companies and industries and so on and so forth. We have some nice discussions with some of you about this on some other systems, right? So now you kind of probably become more secure aware of these things. Quick adversary, quick in logistics, next project due next week. Fill out the feedback form. Last time I checked, it was less 30%, 30% or so. We need 75% to give you bonuses. Okay, so do it as soon as possible. Exam will be on Wednesday. For you guys, will be in class. For MS Online students, will be on Gradescope. It will release at 2 p.m. Pacific time. For you guys, you will have the class time to fill it, and you have to submit it to Gradescope. Don't forget to bring your laptops. For MS Online, they have 24 hours to start, but once they start, they will have the same amount of time as you guys. So I think it would be 1 hour 30. Consider 1 hour 30 minutes as the budget, but it might be slightly less or more. Don't forget your final review papers, which is also due next week, I think. Yes.
Will the final exam be a mixture of short answer and multiple choice, or will it be all short answer?
Probably would be mostly just short answers. I might add a multiple choice, but it's unlikely at this point.
How would you recommend preparing?
Watch the lectures and slides. I think that's what I want to do. Yeah.
Is this lecture also gonna be covered?
No. So this is just a review. So whatever I say today is not going to be part of it.
Or like the papers that we presented gonna be on exam, or like the papers that she.
The presentations, the videos will be, but not the papers themselves.
So basically just read the abstracts should be okay.
Yes.
Hey, yeah, if we forget if we need to like revisit a lecture, can we wear headphones?
You can watch the lectures. You ask, you can actually, yeah. So I've seen people like bringing their headphones and all. So you can watch the lectures, yes. But just keep in mind that internet might be crappy, so don't rely on. But yes, you can. Any other questions? We good? Yeah. Yeah, there are things that are not part of we didn't cover because we keep changing the content. So yeah, if you see that you didn't, so make sure that you study everything. But if you see that something you have no idea about, it's not you, it's us kind of things. Yeah. All right. Oh yeah, what next? If you're interested in any of these research things that I said, you can always contact us. We can do research. Course, as I said, we also always do the embedded capture the flag competition, which is like a very relevant to these things that we cover. It's going on this year, but if you're around next year as well, consider joining. Yeah, thank you guys. Enjoy this class. See you on Wednesday too.